This is part 8 of the mini course Preparing for Organic Chemistry, Intro to Acids and Bases. Here's where we are in the course. We have completed 3 of the 5 topics. This lecture or lesson is on acids and bases. There will be others. It's a very major topic and a large topic in terms of broadness. And of course, we still have to introduce a complete reaction mechanism. But we're making good headway here. Okay, well, first of all, why do we care? Why are acids and bases so important? Why are they one of the 5 essential topics or skills to prepare you to be successful in organic chemistry? Well, here are 3 very typical organic reactions. Take a look at these, and again, we're not learning organic reactivity or functional groups. That's something that you will do in your class, in your course, or something that I will help you with later. Okay, but I want you simply to scan these reactions. See if you can find the acids or bases that are involved. Well, if you identified these 3 substances, then you're doing pretty good, right? Phosphoric acid for the first reaction, ferric bromide for the second, and sodium amide for the third. These are just 3 reactions that I'm using for illustrative purposes. There are thousands and thousands of organic reactions and transformations where the acid or base is involved in some way in the reaction. It might be a catalyst, as it is in the first and second cases, or it might actually be a reagent, as it is in the third case. And I assume you know the difference between catalysts and reagents. I'll probably say something about that when we talk about reaction mechanism. But acids and bases are all over organic chemistry as promoters or accelerators, facilitators of reactions, or as a necessary co-reactant. Now, going back to general chemistry, there are 3 definitions of acids and bases, and here they are. And we're going from top to bottom, or as we go from top to bottom, we're going from the very specific to the very general. The 2 definitions that are of most use to us in organic chemistry are the second and third: Bronsted-Lowry Theory and Lewis Theory. Here's how acids and bases are defined under Bronsted-Lowry Theory. An acid is a substance or species that donates a hydronium ion to another substance, which of course is the Bronsted-Lowry base. A base is a substance that accepts a hydronium ion from another substance, which of course is the Bronsted-Lowry acid. And yes, they're coupled. You can't have one without the other. Just to remind you, hydronium ion is hydrogen minus its single electron, so it's H+. Acid is H+, hydronium. The more hydronium in solution, the stronger, the more acidic that solution is, and the lower the pH. Well, under the Lewis definition, it's even more simple or general. An acid is any electron deficient species. A base is any electron rich species. Very, very general. Okay, so what I show here are 3 Bronsted-Lowry acid-base reactions and their equilibrium position, right? In the first example, we have hydrochloric acid reacting with sodium hydroxide to give sodium chloride and water. In the second reaction, we have bisulfate anion reacting with ammonium ion to give sulfuric acid and ammonia. And in the third example, we have methanol reacting with That's also considered hydronium. When H plus is dissolved in water, the active species is H3O plus, which is also called hydronium, which may be confusing, to give basically a protonated methanol and water. And I have the equilibrium positions denoted with arrows. So in the first example, the equilibrium position is far, far, far to the right. In the second example, it's far, far, far to the left. And in the third example, it's kind of in the middle. So it's one of the sub-skills that you need to develop within the general topic or skill of acids and bases. You need to be able to look at an acid-base reaction and have an idea, perhaps not quantitative, but a semi-quantitative, pretty good idea of where that equilibrium lies. How are you going to do that? Let's take a look. So these are the same examples. What I've done here is I have identified the acid, the base, the conjugate acid, and the conjugate base. Remember, in Bronsted-Lowry acid-base theory, we have the conjugate pairs, right? And so in the first case, for instance, hydrochloric acid is the acid, and water is the conjugate acid of hydrochloric acid, right? Sodium hydroxide is the base. Sodium chloride, or chloride really, is the conjugate base of sodium hydroxide. Right, the sodium ion is a spectator. In the second example, bisulfate anion is the base, ammonium ion is the acid, and no, the order doesn't matter, right? And then sulfuric acid on the product side is the conjugate acid, and ammonia is the conjugate base. Okay, and so the definition of conjugate, or how to correctly specify the roles of the four individual species in a Bronsted-Lowry acid-base reaction, is simply follow the proton, follow the hydronium ion. Right, in the first case, the H in HCl is clearly being transferred to the OH in sodium hydroxide. And that's all you need to know to make the correct assignments. In the third example, again, you can see the H plus in ammonium is being transferred to bisulfate, and then you can make the correct assignments. Now, what I also show here is, I asked the question, how are you going to be able to determine semi-quantitatively the position of equilibria of, say, a given or proposed acid-base reaction? Suppose you are proposing an acid-base reaction as part of a proposed mechanism that you're asked to write. It won't do you any good to propose an acid-base reaction that has no chance of forming products, right? So how are you going to know? Well, remember the position of the equilibrium, and this is KAB, right? If KAB is much greater than 1 and the equilibrium lies far to the right, that occurs when the conjugate acid is much weaker than the acid. You can see that in this slide, right? Or to put it another way, when the pKa of the conjugate acid is much greater than the pKa of the acid, the equilibrium lies far to the right, okay? Look at the second example. The second example is a case where the equilibrium lies far to the left. That's because sulfuric acid is a much, much stronger acid than ammonium. Okay, so this is all consistent. All right, now let's make sure you know what pKa means. That's awfully important. Okay, so pKa, of course, refers to Ka, and Ka is the Bronsted-Lowry acid-base equilibrium for the reaction between a Bronsted-Lowry acid and water. Water is always the base or proton acceptor, right, in a Ka reaction. And I apologize, I don't have the equilibrium arrows here. I should, but I don't. Imagine that they're there. All right. And so again, the definition of Ka, right, the mass action expression for Ka is given by the stoichiometry of the reaction, and that's simply the product concentrations A minus times hydronium divided by HA. Or for an acid that is of the form HA plus, it's A times H3O plus over HA plus. Now remember, we don't include water in the equilibrium expression since water is the solvent and its concentration is essentially constant. Now pKa is the negative log of Ka. That's what the P operator in chemistry means, take the negative log of. It's an operator, right? And so it follows that Ka is equal to 10 to the minus pKa. So what you can see here is that as pKa becomes greater, right, becomes more and more positive, that means that Ka, right, becomes smaller and smaller because of how pKa is defined, right? Or again, to look at it the other way, you can see Ka is equal to 10 to the minus pKa, and so for a very large and positive pKa, you have a very large negative exponent, which means you have a very small Ka. Okay, so large, very positive pKa, and yes, pKa's can be negative. Large and very positive pKa's indicate a very, very weak acid. Very low or negative pKa's indicate a very, very strong acid. All right, so I'm going to stop this here. There's a lot more to do with acids and bases in organic chemistry, especially once we start talking about reaction mechanism. But I'm going to break this up. I'm going to stop this here, and we'll continue our discussion of acids and bases. And hopefully this is review for most of you.